Recently, I bought myself this big autotransformer. In case you do not know, then let me tell you that such a device can take mains AC voltage on the inputs and transform it into a lower adjustable AC voltage on its outputs. This can come in handy when you want to test your DIY electronics projects with a lower AC voltage, like I did during a previous video with a Tesla coil. Now, I actually owned a smaller autotransformer before, but it was only capable of delivering 500 watts on its outputs, which is much less in comparison to the new one that can output 3000 watts. And let's not talk about how I connected mains wires to my old autotransformer, which is now way easier and safer to do with the new one. So, in a nutshell, everything is better now. And I just wanted to show off. Right? Well, not exactly. Because oftentimes when I plug the new transformer into an outlet, my circuit breaker trips. Only due to pure luck, I can power up the new autotransformer from time to time. And that is why in this video I will not only demonstrate why my circuit breaker keeps tripping, but also how I created a DIY AC Softstarter, which, like the name implies, can softly start up my autotransformer every time without tripping my circuit breaker. Let's get started. This video is sponsored by JLC PCB. Feel free to visit their website jlcpcb.com to not only find out what awesome PCB and assembly services they offer, but also to easily upload your Gerber files and thus order affordable and high quality PCBs quickly. First off, why not open up my old autotransformer in order to find out how it works? As you can see, it mainly consists of one big ferromagnetic core, around which partly enameled copper wire is being wound. And I say partly because a sliding brush seems to make electrical contact with the wire, which is connected to the output terminal of the transformer. The input terminal, however, is connected to the whole length of the copper wire, which therefore means that the diagram of this transformer looks something like this. Now, like probably already mentioned 1000 times before, we are dealing with a transformer here, whose job it is to obviously transform high mains AC voltage on the inputs to a lower AC voltage on the outputs. And if you have no clue how a transformer works, then make sure to watch my video about the topic. But anyway, this autotransformer type is special, because it only uses one winding instead of two, like a traditional transformer does. Its functional principle, however, is still pretty similar, with the output voltage being the multiplication of the input voltage with the turns ratio. And since we are using a movable brush for the secondary turns, we can fine-tune the output voltage very precisely. This design also has the advantage that it requires a smaller core and fewer windings in comparison to a two-winding transformer, which makes it smaller, lighter and cheaper. But on the other hand, there's no electrical isolation between the inputs and output side of the transformer, which means that if you hook up mains voltage incorrectly, then you can get a nasty shock if you're not careful. And that brings me to a small warning that we're dealing with mains voltage here, which if mishandled can lead to major injuries. You have been warned. But anyway, now that we more or less understand how the autotransformer functions, why exactly does it trip my circuit breaker? It must have something to do with the current, because protecting from overcurrent is in the end the main job of circuit breakers. So, to investigate, I hooked up my energy multimeter to my big autotransformer. And after powering the system, the transformer seems to draw an apparent power of 27 volts ampere with 13 watts of real power, so nothing suspicious here. Next, to further investigate, I added a 1 ohm current shunt in series to the live wire, whose voltage I monitored with my oscilloscope. Because, as you might know, the current flowing through such a resistor is the voltage across it divided by the resistance. And since the resistance is 1 ohm, the monitored voltage will equal the flowing current. But anyway, after once again powering up the system, my oscilloscope found the culprit by recording a fast voltage peak with a maximum value of 38 volts, so 38 amps. Now, not only my autotransformer does create such a current spike problem at the power up though, because all kinds of motors do also create a similar problem. The reason is the inductive characteristic of those devices. You see, when no current flows through our coil or winding, then the initial current flow is only limited by the resistance of the winding, which is in my case 2.2 ohm. So, if we due to bad luck connect the transformer to the grid at the highest peak of our mains voltage waveform, which equals a value of 325 volts, then we would get an initial current spike of 148 amps, which is why the circuit breaker trips. But, and here's my first solution, if we power the transformer near the 0 point, then the initial current spike will be much lower and hopefully not trip the breaker. And due to the now flowing current, the magnetic field also builds up, which opposes the current flow and thus creates an additional resistance which will lower the current to the previously measured values. And fun fact, my smaller autotransformer did not come with this problem, since it featured a way higher real resistance. Because the more power your transformer has to output, the lower its real resistance will be. Okay, now to solve this problem, we basically need a circuit that turns on our appliance near the 0 point of our mains voltage waveform. The easiest way to do this would be with such a solid-state relay. After connecting it to mains voltage and the autotransformer according to this little schematic, we can see that whenever I hold down the push button on the input side, the autotransformer powers up without a problem. And if we observe the applied voltage waveform on the oscilloscope, then we can see that the transformer does in fact only switch on near the 0 point. The reason for that can be found in the schematic of the solid-state relay. As you can see, it uses a triac in order to turn on the loads, but it can only do so near the 0 crossing point, which basically solves my problem. And if you want more information about such solid-state relays, then make sure to watch my video about it. But anyway, even though this solution works for me, I was not yet happy with it, because every inductive load is different, and yours might even trip your breaker when it switches at the 0 crossing point. So instead, I wanted to create a proper soft starter that uses phase angle control in order to slowly increase the RMS voltage value for the connected loads. That is why I looked through all the components I had laying around and came up with this schematic. The heart of the system is an Arduino, which notices when a 0 crossing point is reached, and then it waits a slowly decreasing time delay before it activates a triac. The 0 crossing detection is achieved by an optocoupler, which at low voltage values at the mains input sides does not activate, and thus the output of it at the Arduino side gets pulled up. And this is how the detection looks like on the oscilloscope. Then I also added a red LED which indicates that the system is ready, a push button to start the soft start sequence, and a green LED to indicate that the soft start process is over. And with the schematic being completed, I gathered all of the required components for the build and started soldering them to a perf board. The circuit assembly was not really hard to complete, but all in all I spent around 3 hours working on it before it was done. So next I moved on to the Arduino programming, which was also pretty straightforward, except maybe the timer configuration for the phase angle control delay. But you can read comments about those lines if you download my code from the video description. Anyway, after uploading the codes, I wired everything up for a first test with a light bulb, because this way the soft start is easier to observe. And as you can see, the light bulb slowly lights up, and on the oscilloscope we can see how the phase angle control works flawlessly. So next I did the same test with the autotransformer, which also passed it without any problems. That is why I continued by designing a housing for the project in Fusion 360, 3D printed it with my 3D printer, attached an outlet to it along with an IEC socket for the inputs, added the push button and LEDs, wired everything up, and finally closed it all with the lids. And as you can see, everything still works fine without any problems. With that being said, I hope you enjoyed this video and learned something new along the way. If so, don't forget to like, share, subscribe and hit the notification bell. Stay creative and I will see you next time!